Now in this video we'll try to understand about the basics of Newton's three laws, first, second and third law. So I'll try to define the three laws in the easiest way possible, and also which comprises of the entire meaning of the laws. And I will put the first law this way. So how can I define the first law? So the first law states that, so can I define the first law? So I can define the first law this way. If the vector sum of the forces acting on the body is 0, if the vector sum of forces is 0, if the vector sum of the forces, or sometimes we also call it as the net force, then the body remains unaccelerated. Then the body remains unaccelerated. What is meant by this? The body remains unaccelerated, or I can say unaccelerated is nothing but it means that the body will not have any kind of acceleration. Or I can say, so if I put these into equations, if f is equal to 0, then a will be 0. Okay, this is what is meant by the Newton's first law of motion. We'll try to understand this first law well by taking a small example. Or first, let's say we have a body. We have a body of certain mass, whatever the mass is. We are not concerned about the mass. Let's say we have different forces acting on the body. Okay, something like this: F1, F2. I hope you already have the idea that the force is a vector quantity, where apart from its magnitude, the direction is also important when we speak about any force. So speaking about the magnitude alone doesn't make any kind of meaning when speaking about the force. So apart from the magnitude, direction is also very important, or we can say both magnitude and direction are necessary whenever we specify about force or about any other vector quantity. So when I have a mass m, and let's assume in this situation it is acted upon by three forces, F1, F2 and F3, and their directions are also mentioned. Now let's say if the vector sum of the forces, acting on this body is equal to 0, if the vector sum of the forces acting on this body is equal to 0, then if this is possible, then only then I can say acceleration is 0. Acceleration of the body is 0. So we'll try to understand what is meant by acceleration being 0. So if the net sum of forces acting on the body is 0, then I can say acceleration is 0. Okay, and we can also say it in the opposite way. If acceleration of the body is 0, then we can definitely conclude that the net force acting on the body is 0, or the vector sum of all the forces acting on the body is 0. Okay, now let us try to understand what acceleration equal to 0 being means. What is meant by acceleration being equal to 0? Now we'll try to understand about its meaning. So in order to understand that, let's take a simple example. Let's take a small example. Let's say we have a body of mass m, initially moving with 5 meters per second and in the right direction, and let's say we have another body of the same mass m, but initially it doesn't have any velocity, and velocity of the body is equal to 0. So in the first situation, in the first situation, the body has a velocity 5 meters per second in the right direction, and let's say different forces act on the body, and the sum of all those forces becomes equal to 0. So similar to these three forces, let's say we have a few forces acting on the body, first body, which was initially moving with 5 meters per second, and if the sum of all those forces is equal to 0, then according to the Newton's first law, we can say that acceleration of the body will be equal to 0. So if we have, I did not mention the forces here, but assume that there are different forces acting on this mass, Okay, I'm not drawing the forces here because I don't want to make the diagram more complicated. So the arrow indicates the direction of its velocity here, and the magnitude of the velocity is represented by 5 meter per second. So here, see, I have not represented the forces, but let's say we have three different forces, F1, F2 and F3 acting on the body, and the sum is equal to 0. Then we can say acceleration is 0. Then what we mean by acceleration being 0 in this case is, that means the body will continue to go in the right direction forever. So the body will continue to go in the right direction forever. That means its direction of velocity doesn't change, and as well as the magnitude of velocity doesn't change. Or we can say that the body continues its uniform motion. Okay, it undergoes a uniform motion or a uniform velocity motion. So if a body initially has certain velocity, it will continue to move with the same velocity when the net force acting is 0, because acceleration is 0. Acceleration, we define it as the rate of change of velocity. Since acceleration is 0, so there is no change in velocity. Okay, so we'll have acceleration only when there is some change in velocity. Okay, so since there is no acceleration, there will be no change in velocity. The body will continue to move with the same magnitude of velocity and as well as the same direction of velocity. The important thing here to understand is that velocity is a vector quantity. So when I say velocity is not changing, I mean to say that both direction and as well as the magnitude are not changing. So that's what happens when a body initially has certain velocity and different forces acting on it. If their sum is 0, then acceleration will be 0. So the body will continue to move with the same velocity. So what if I have the same mass, but instead of having certain velocity, if it's initially at rest means it's not moving, so I can conclude that its velocity is 0. And still, if the forces are acting on the body, something like these three forces, and the same thing here also, I am not mentioning any forces in this diagram because I don't want to make it look complicated. But imagine that three forces are acting on the same body again in the second situation, and their sum is also equal to 0. Then from the Newton's first law, we can say acceleration is 0, or there will be no change in velocity. So initially velocity is 0 and velocity doesn't change because the sum of all the forces is 0. So this body, it remains at rest forever. So it will be at rest all the time when the sum of all the forces acting on that second block is 0. So this is what we can understand from the Newton's first law. So what it basically says is, if the vector sum of forces is 0 acting on a body, then the body remains unaccelerated, or it doesn't have any acceleration. Or in simple terms, we can say that if F is equal to 0, or sum of all the forces acting on a body is 0, then acceleration of the body will be 0, and also vice versa. We can say if acceleration of a body is 0, then we can conclude that the total force or the resultant force or the net force acting on the body is equal to 0. So this is about the meaning and the concept of the first law, and I'll explain some examples and some applications regarding this in the next video. But for now, we'll proceed to the Newton's second law, the basic meaning and the definition of the Newton's second law. It's worth noting here that we can sense that there is some kind of relation between force and acceleration from the Newton's first law. So we'll come to that relation in the Newton's second law. Okay, so in the first law we have there is no direct relation between force and acceleration, but we can directly sense that there is some sort of relation between them. So we will try to get that relation between the force and acceleration in the Newton's second law. Okay, how one thing is related to the other. Okay, so we'll try to understand how the force and acceleration are related to each other. Okay. Okay, so now we'll proceed to the Newton's second law. So First, let me define it. Newton's second law. These three laws of Newton's are very, very important in the context of physics, because we'll be coming across them in each and every topic in physics, and they're very, very important because we come across forces everywhere in any kind of body or in any kind of situation. So it's worth noting that you need to understand these three forces very well. Only then you can understand the rest of the physics very well. If you fail to understand these Newton's laws, you fail to understand most of the physics. It doesn't make any sense. Okay, now let me define Newton's second law. So before defining Newton's second law, I'll define something called as momentum of a body, or linear momentum of a body. Linear momentum of a body. So I'll not discuss much about the linear momentum. I will just be writing its relation. So it is generally represented with P, okay, P, where that linear momentum is the product of mass and velocity of a body. M and V bar, where M is the mass of the body. M is a scalar quantity. I mean, mass is a scalar quantity. It only has magnitude. It doesn't have any direction. But coming to the velocity, we know that it's a vector quantity. So it's something like a scalar M multiplied to the vector V. So the product will also be a vector. So from this, we can conclude that momentum is also a vector quantity. Okay. And we can also see that the direction of momentum is in the direction of the velocity. Okay. Direction of, if you have idea about the vectors, then you can directly sense that direction of velocity and direction of momentum will be the same. Okay. Now after defining this momentum, we'll directly go to the Newton's second law. The definition of the Newton's second law. We can define Newton's second law this way. The rate of change of momentum, the rate of change of momentum of a body, the rate of change of momentum of a body is directly proportional to the force acting on the body. Directly proportional to the force acting on the body. I've already told you that there is some kind of relation between the acceleration and force, and we'll try to get that relation by using this definition of Newton's second law. So how this rate of change of momentum is connected to the force is given by the Newton's second law. Suppose if we have a body, and if there are different forces acting on the body, then I already told you that if there are, from Newton's first law, if there is some set of forces acting on the body, if the sum of forces is equal to 0, then acceleration is 0. If the sum of forces is not equal to 0, then acceleration will be a non-zero quantity. So in this case, when there is some net force acting on a body, we can definitely come to a conclusion that there is an acceleration. So there is some net force acting, there is an acceleration. Acceleration changes the velocity. So when the velocity changes, here when V changes, P also changes. So momentum is changing. So this is the relation. So when there is some net force acting on a body, there will be some acceleration acting on the body. So when there is some acceleration on a body, then velocity of the body changes. Velocity of the body changes. The change in velocity of the body leads to a change in momentum. So this is how the momentum change is connected to the force. So we define the rate of change of momentum is directly proportional to the force acting on the body. So if we are not thorough with the calculus, this rate of change and all those things, in the end we'll get to a simple relation between the force and acceleration. If you do not have any proper idea of this rate of change of momentum, then the end result of this Newton's second law can be defined, which will be directly helpful and very easy to understand in many ways. But for a few situations, you may have to use this method. Okay, let's proceed. So let's try to put this sentence in the form of an equation. So I'll put that definition. rate of change of momentum is directly proportional to the force acting on a body. Force acting on a body. Or the momentum can be written as m into v bar. Or in order to get rid of this proportionality symbol, I will write some constant f bar. Okay. Or I can write this something like this, m into dv bar by dt. So if you have some basic idea about the calculus or the differentiation, what I'm writing makes sense to you. But if you do not have any idea, it doesn't make any sense. So even if you don't understand this part about the differentiation, then the end result, which is going to be very easy, will be very easy to understand. And dv bar by dt is nothing but the rate of change of velocity. So from kinematics, it's nothing but acceleration plus dm by dt, or the rate of change of mass. So if you have certain body whose mass is not changing with time, then this thing comes out to be 0 when its mass is not changing. So I can equate it to 0, and this becomes 0 is equal to k into f bar. And this constant k is taken to be 1. There is a simple reason behind the k being equal to 1, but I will not be mentioning that here. But it's very easy to understand, and it also makes sense when you understand why k is taken equal to 1. A very simple reason, and very confusing at times when you don't properly look at it in the right direction. Okay, so we can write this as m into a bar is equal to f bar, or force is equal to mass times acceleration. So from the definition of the Newton's second law, we have been able to get a relation between force and acceleration. So even if you don't understand the entire differentiation part, if you could remember this relation between force and acceleration, it will be helpful in many cases directly. You may not understand this, but it's worth noting that force is mass into acceleration. Even if you just remember this, it will be helpful in many cases. But if you want to understand a lot of physics, a lot of subject, then it's worth understanding this. But if you are a beginner, it's better to start just with this. Force is mass times acceleration. So that's what I told you. So we have a relation. The first law tells us that there is some kind of relation between mass and acceleration. Force and acceleration. The second law gives a relation between force and acceleration. And here, one more important point about this is, here note that this is valid only when the mass of the body is not changing. Dm by dt is equal to 0. It means that m is constant, or mass of the body is constant, or when the mass of the body is not changing. In the entire physics, most of the times, in most situations, the mass of the body doesn't change. But in a few cases, you may come across situation where mass is changing. But those cases are very, very few. Even if you don't remember this, it's not going to be a big problem. But if you want to understand the physics to its depth, it's worth remembering this. Okay, this is about the Newton's second law. So definitely, whenever there is a force acting on a body, so whenever I mean by f bar, I mean the resultant force acting on the body definitely influences the acceleration of the body. This is about the Newton's two laws. Let's get to the Newton's third law. Newton's third law. Newton's third law, it doesn't involve anything in the equations. It doesn't have equations. So just let's write it here itself. Let me use this space in order to explain the Newton's third law. Newton's third law. So very easy one, and sometimes very easy to use this in a few situations or in a few problems. So I already told you that I'll be explaining the problems and the applications in the next video or the upcoming video. For now, I'll just explain the meaning of the Newton's third law. Newton's third law. Okay, what is meant by this? We often use it most of the times. Something like we define it this way. So for every action force, there is an equal and opposite reaction. For every action force, there is an equal and opposite reaction. It's so easy to remember the definition, but so difficult to understand in a few situations. Okay, for every force or action force, you can call whatever you wanted, for every action force there is an equal and opposite reaction force. Equal and opposite reaction force. So in order to understand this better, I will give you a little example. Okay. So before going to this, I just want to give you a simple explanation in order to understand this better. Let's say I have a body, have something. In order to feel this better, let's take some heavier body or something like a heavy book. Okay, and just try to hold it in your hand. Just try to hold it in your hand. Okay, so most of the times physics is all about imagination. So try to imagine that what happens when you just try to release the book. So if you try to release the book, it just falls down and touches the ground. It reaches the ground or the floor. Okay, imagine that you are holding heavy book, and what happens when you release it? It falls down and touches the ground. That's what happens when you release the body. Okay, but whenever you are holding it, you are not letting it fall. We all know that the gravitational force acts on the body in the downward direction. Right? So we all know that there is some downward force acting on the book, but it's not falling down whenever we are holding it, because we are applying some force on it in the upward direction. So note this point, we are applying some force on the book in the upward direction, right? And I think whenever you hold the book, it tries to pull your hand downwards. You might have experienced it when you hold heavy objects. They try to pull you down. So when I hold the book, we are applying a force on the book in the upward direction, and we are not letting it fall. So we are applying a force on the book in the upward direction, and we can also feel that it is trying to pull my hand in the downward direction. So observe that here we are applying some force on the book in the upward direction, and book is also trying to pull our hand in the downward direction by applying a force in the downward direction. So there is a force acting on the book due to hand in the upward direction, and there is a force due to book on the hand in the downward direction. So in this case, these two forces, the force exerted by the hand on the book in the upward direction and the force exerted by the book on the hand in the downward direction, these forces form an action-reaction pair. Okay, I'll just try to draw the diagram in this case. Let's say this is my hand, and I am not good at drawing diagrams. This is book, this is my hand. Now if you look at the book, we are applying a force on the book in the upward direction, some F. So, and we are not letting it fall downwards, because there is a gravitation force acting on the book in the downward direction. And in order to avoid it fall down, so we are applying some force F on the book in the upward direction. So if you take your hand, the book is applying some force on your hand in the downward direction. You will definitely feel this when you hold a heavy book. It is always trying to drag your hand downwards. Okay. So here, these two forces, force acting on the book in the upward direction due to hand F upwards, and force acting on the hand due to the book is F downwards. These two forces can be called as action-reaction pair. So any one of them can be called action force, and the other one could be called reaction force. So what we can say from this is, forces always come in pairs. Okay, always come in pairs, something like this. We can call these forces as action-reaction pair. So there is always a force, and there is always a pair accompanied with it. Okay, so what I can say is, forces always exist in pairs, but they need not act on the same object. In this case, if we take this action-reaction pair, one of the forces is acting on the book in one direction, and the other force of same magnitude but acting on the hand in the other direction. And one more important point about these four action reaction pair is they have equal magnitudes. They have equal magnitudes and they act on different objects. They act on different objects and they are always in opposite direction. So we have mentioned that they are opposite in direction in the definition itself. So forces, so what we need to understand from the third law is forces always come in pairs, something like this. We can call them action reaction pair. You can call one force as action, okay? Any force you can call either this force or this force as action force, and the other could be called as a reaction force. So they come in pairs and they have equal magnitudes. See, they have equal magnitudes and they act in opposite directions, okay? The force on the book is acting upwards and the force on the hand is acting downwards. So this is about the Newton's third law. So these three laws, the first, the second and the third form the basics for the classical physics or basic physics. So if you fail to understand these things, you fail to understand most of the physics. So try to think about these things. They do not make sense that easily for the first time. In order to understand these things, you need to have a little bit of imagination and you need to think about them a little. So in the next video, I will explain some applications and problems related to this and how to apply this to real case scenarios or real life scenarios. Okay.